Celebrating over 100 years, the Air Force Institute of Technology is the Air Force's graduate school of engineering and management, as well as its institution for technical professional continuing ed. Dayton's heritage and industrial base in aeronautics and aviation, coupled with its close proximity to AFRL and NASIC, provide an unparalleled scientific and engineering research and education experience. AFIT focuses on producing future Air Force leaders. A few notable AFIT alumni consist of 3 Doolittle Raiders, a Tuskegee Airman, and the first pilot to achieve Mach 3. Now, let's hear from an educator about Industry 4.0.
Morning, everybody. Welcome to our second keynote of the morning, Industry 4.0 and the Connected Supply Chain. My name is Tom Joes, Air Force Account Manager for Software AG Government Solutions. We are a COTS software publisher. Our Cumulocity IoT platform enables IoT and analytics at the intelligent edge and across the industrial network, while Web Methods integrates the flow of data and transactions through the extended enterprise of legacy systems, cloud applications, SaaS providers, and external partners. Our products are perennial leaders among the capability assessments published by major industry analysts. Our keynote for this session, Dr. Ken Laparo of Case Western Reserve University, is an IEEE Life Fellow, American Institute of Medical and Biological Engineering Fellow, and the Arthur L. Parker Professor in the Department of Electrical and Computer Systems Engineering, with academic appointments in the Departments of Biomedical Engineering and Mechanical and Aerospace Engineering at Case Western. He is the founder and faculty director of the Institute for Smart, Secure, and Connected Systems, or ISACS, and is the co-academic director of the Internet of Things Collaborative, or IOTC. Please extend a warm welcome to Dr. Laparo.
Thank you. And sorry I can't be there in person. I had some commitments here in Northeast Ohio. So I'm coming to you in a virtual format, which I think most of us are pretty familiar with over the last 16 to 18 months. So next slide, please. So what I wanted to do is to start out with talking a little bit about some definitions. There's a lot of acronyms that floating around related to the Internet of Things and the Industrial Internet of Things. And so it's probably good to spend a few moments to focus on what these ideas actually mean, what the interrelationship between them is, and then I'd like to talk about what we're doing in Northeast Ohio through ISACS and the IoT Collaborative, and then begin a journey to discuss some opportunities and challenges around IoT, IIoT, Industry 4.0, and how these relate particularly to cyber-physical systems. So when we talk about the Internet of Things, or IoT, we're really talking about sensors and actuators, connected devices and systems, and we're talking about a sort of ubiquitous communication network that could be wired or wireless, that's connecting the devices, that's allowing the interconnectivity and the flow of data and information, both from the perspective of using data to understand the current state of the environment or the system, but also providing an opportunity for command and control to be transferred back to the devices. When we talk about the Industrial Internet of Things, or IIoT, we're really focusing on machine-to-machine communications and interactions, and we're talking about applications in the manufacturing sector, applications in energy and utility systems, oil and gas, and the rest. So we're really talking about industry foci related to IoT. And the idea is that IIoT sits inside the general framework of IoT. And then there's Industry 4.0, or I 4.0, which really is IIoT applications that focus primarily or specifically on industrial control, manufacturing, and the automation sector. So I 4.0 is a subset of IIoT, which is a subset of IoT. And all of these, IoT, IIoT, and Industry 4.0, all have a relationship with cyber-physical systems. Cyber-physical systems describes the relationship or interaction between physical entities that are networked and interacting together. So there's a cyber layer and there's a physical layer, and the cyber and the physical layer are dynamically interacting. So cyber-physical systems are simply a network collection of physical entities or physical systems. Next slide, please. So when we talk about the Internet of Things, some typical examples of the Internet of Things are, on the left-hand side is a nice image that I found that relates to how we as individuals, potentially with wearable devices, are interacting with through the Internet in order to provide data relative to very common or well-known human activities. And so a typical example is a wearable for motion sensing, potentially PPG, that is being able to pick up heart rate, being able to pick up body temperature, being able to say something about motion and speed of motion, and also GPS saying something about position, and moving this data through the internet to various cloud resources, which allows us to either interact with the data after the event or allows others to interact with our data. On the other side, we also have other sort of applications of IoT, where we allow the connectivity of various other devices or systems through the internet to provide data and opportunities for us. The IoT applications can include single networks, wired or wireless, or multiple different networks that are adhering to different communication protocols, have different sort of application venues, and provide different ways of actually connectivity, but also different ways for protecting and securing data. Next slide, please. So why the Internet of Things? Well, according to a source through McKinsey Global Institute, the Internet of Things has a potential huge economic impact, somewhere between $2.7 and $6.2 trillion up to the period of 2025. So it ranks third in terms of sort of priorities where economic investment and economic impact is going to occur. And there's a lot of focus, as you well know, in IoT, especially on the consumer devices, from individuals to smartphones to homes. Next slide, please. So let me talk a little bit about ISACS, the Institute for Smart, Secure, and Connected Systems. So Case Western Reserve University is an R1 or a Research 1 university in Northeast Ohio. And next slide, please. And when I was chairing the Department of Electrical Engineering and Computer Science before we split, we were doing a strategic planning exercise trying to find how 5 academic programs could interact not only educationally, but also how we would interact in the research front. Next slide, please. So we formed the Institute for Smart, Secure, and Connected Systems as a research and educational focus that would provide an opportunity for interactions between electrical engineering, computer engineering, systems and control engineering, computer science, and data science and analytics, which were the 5 programs that I managed in that department. Next slide, please. Next slide. And we approached the Cleveland Foundation, which is a philanthropic organization in Northeast Ohio, one of the oldest, actually, philanthropic organizations in the country, to look about funding this opportunity of Isaacs at the university and reaching out to the region. Next slide, please. At that same time, Cleveland State University, which is a couple of miles down the road from Case, was also talking to the Cleveland Foundation about a cybersecurity and privacy institute coming out of the law school at Cleveland State. And the Cleveland Foundation asked us to look at building a public-private university partnership, next slide please, which allowed us to collaborate in Northeast Ohio and develop a focus in the region around IIoT. Next slide, please. And as a result, we formed what we call the IoT Collaborative, which is a two-university partnership that also engages with our manufacturing partners, our healthcare partners, our economic development partners in Northeast Ohio. Next slide, please. The broad focus of Isaacs and the IoT Collaborative is in two major areas. One is in future manufacturing, including Industry 4.0, with a focus of Industry 4.0, not at the large corporation level, but at the small and medium-sized manufacturing companies. And if you look at Cleveland and about, I don't know, maybe around 50 miles to 100 miles radius from Case Western Reserve University, which is in University Circle, we've got something like 7,000 small and medium-sized manufacturing companies in that area. Very interested in advanced simulation and leveraging both machine learning and physics-based modeling to help Industry 4.0 and IIoT. We have a lot of expertise and activities in computational materials using computerized methods to support materials design and the development. And we're interested in hybrid manufacturing, which combines various manufacturing processes of different types in order to achieve greater manufacturing efficiency and better product quality. Next slide, please. We're also interested in connected health as a parallel stream. I won't spend too much time on this side, but it takes the idea of Industry 4.0 or I 4.0 and translates it to Care 4.0 in a connected health environment. Next slide, please. We have a lot of activity in the region. I'll only summarize a little bit of it. We just were selected to establish a Smart Manufacturing Innovation Center, or what's called a SMIC, in Northeast Ohio. This is coming out of the Clean Energy Smart Manufacturing Innovation Institute, SESMI, which is a DOE-funded national institute around smart manufacturing. We have a lot of activities in the smart manufacturing area, and I'd be happy to talk more about that in the future. Okay, next slide, please. So what are the core sort of technology disciplines around IoT? Well, sensing, signal processing, control, automation, and higher level decision making are absolutely essential. I think, as you've already heard before, embedded systems and edge computing are absolutely essential as we move from cloud infrastructure, which were the most popular sort of ways of having data accessible, to now moving to the edge and having much more activity at the edge, both in terms of data management and algorithmic development, as well as local control. Communications and networks are absolutely essential to provide a connected enterprise, from devices and systems, including sensors, control elements, through the edge to the cloud. Software engineering and new software engineering methods and principles. Data engineering is an important part of it because we generate a lot of data, and before you can properly do analytics, you must have the data managed and transformed and formatted in the right way. Visualization, augmented, and virtual reality now become a critical part as we look at using advanced simulation tools and computational models in order to help improve not only the visibility of these processes through data integration and analytics, but also in terms of how one includes, in an active way, humans in the loop. A lot of buzz about artificial intelligence and machine learning, of course. They have their place in IoT and IIoT, and there's also a lot of concern and interest in how ethics in AI and machine learning have a key role in IoT and IIoT. And finally, digital transformation and innovation is critical. And this not only involves what happens, let's say, on the factory floor or at the network level, but this also includes cultural changes that have to occur at the industry levels in order to properly embrace these new technologies, methods, and ideas. Next slide, please. If we look at a common IoT architecture, at the edge, we have sensors, actuators, devices connected to other devices through machine-to-machine communications. We have a hub, which sort of aggregates this data and then allows this data to move to the cloud. The cloud can be related to buildings or factories or hospitals or campus or nationwide and global networks. At those levels, we have dashboards and analytics where AI and ML are used to provide insights. We have decision support capability, and a huge part of this is third-party integrations and interactions in order to bring these technologies and methods into the applications. What's common and sort of shared capacity across these are problems related to data acquisition, acquiring the data from physical devices. Security and privacy are absolutely essential. Image acquisition and analysis. We generate a lot of time series data, and how that time series data is encoded and stored and used is critical. You need to be able to manage selected data sharing in order to improve outcomes for individual devices or collected devices and systems. Real-time opportunities are key, where we're looking at opportunities for not only closing local control loops for real-time control, but also looking for providing decision support for humans in the loop for more real-time decision making. And we have, through this architecture, the opportunity to take advantage of real-time data for analytics, diagnostics, and prognostics. Next slide, please. So when we talk about IoT, we have opportunities in communications with connected devices involving individuals and their own devices. Huge opportunities in the retail setting, where we allow people to connect to different retailers with opportunities for shopping. As we know, if we look at what's happening in terms of how the pandemic has changed how we now approach shopping and retail interactions. We need to manage this whole connected world, and that managing requires key thoughts about security and privacy. Security not only on the devices, but privacy of the data that's acquired. Applications to vehicle and vehicle communications in order to improve transportation systems and throughput. Industrial applications, which we'll talk about next in terms of IIoT, and huge medical applications that allow patients to now be 24/7 connected to their physicians, and good opportunities for management of acute and chronic diseases through medical informatics platforms. Next slide, please. The Iot Technology Roadmap started early on with very simple ideas of how we track devices or packages, let's say things like RFID for routing, and now is moving up through the areas of surveillance and security, the ability to locate people, and the whole areas of teleoperation and telepresence, which allows us to the ability to monitor and control when we are distant from the objects that we're trying to work with. And the idea is that technology has been developing along with these various applications, with the opportunity of taking advantage of AI, ML, the ideas of software agents and advanced sensor fusion applications to improve our interactions with the physical world and improve our ability to take advantage of these assets in our daily life. Next slide, please. Now, the Industrial Internet of Things is a subset of IoT. It's a network system. It includes physical assets or cyber-physical assets, sensors, actuators, and devices, and again, cloud and edge computing platform. Opportunities for real-time intelligent and autonomous access, collection, analysis, communications, and the ability in real time to exchange data between devices, process, products, and service to improve information flow. Operations in the industrial environment can help us improve overall production value and product quality, and they can help increase the efficiency of both the production system, reduce manufacturing costs by allow us to better utilize the raw materials. We can reduce energy consumption by proper scheduling and managing of industrial processes within a manufacturing enterprise, and we can improve our build-to-order cycles in order to shorten the time at which raw materials are transformed to products. Next slide, please. The IoT development stages are commonly sort of moved into 4 different stages. The first stage is related to the sensors and actuators and how those sensors and actuators are connected to and interacting with the physical devices within the manufacturing enterprise. The second stage is really the idea of the gateways, that is the hubs and the ability to aggregate data, transform analog or continuous data to digital data, and support measurement and control on the factory floor. The third stage is really at the edge and moving what maybe we thought would happen at the cloud, but because of privacy, security, and latency issues, we want to move those functions down to the edge in order to provide an opportunity for analytics, both from the perspective of analyzing the data, but also providing local control and closing much faster control loops at the edge, and then moving things ultimately to data centers, to the cloud, where we're looking at providing maybe more at an enterprise level the interaction and integration of data supported by analytics and management services, as well as archiving the data for future use. Next slide, please. Next slide, please. The IoT architecture is much like the IoT architecture that I talked to you before. We've got actuators and sensors connected to devices. We've got controllers that are locally hardwired, usually to the devices. We then have gateways with communication protocols between the controllers that are both providing a data pathway to the edge devices, as well as an opportunity for analytics at the edge devices to provide commands, set points to the controllers. The edge devices then are connected to a platform. That platform provides a secure and shared message bus, which allows us to exchange data from the higher level tiers at the enterprise level through that platform in order to move through the IoT devices, through the controllers down to the manufacturing floor. This is a distributed architecture, and as we move up the hierarchy, the latency increases, but we also have the opportunity for increasing data aggregation, so we can bring in data from many disparate sources down on the factory floor, and where we might be localizing control at a device level. As we move up the hierarchy, we have an opportunity of more coordinated and adaptive and supervisory control, where we're now simultaneously managing multiple processes within the system that are connected physically through the physical infrastructure of the plant itself, but are not networked together, but are providing data independently. Next slide, please. The IIoT opportunities are significant. Real-time monitoring and control, which we've seen through this pandemic, is a huge opportunity and an important asset for operations. Predictive diagnosis, the ability to take data and using both empirical models as well as computational models and data-driven models that allow us to get better visibility into the process and improve our ability to detect, diagnose, and prognose what's happening in the plant. We move from time-based maintenance to condition-based maintenance, where we're looking at the health of a device, and rather than, let's say, replacing a tool on a machine tool because it's been running for 100 hours and we know 100 hours is its normal life, we monitor the tool wear dynamically in real time and only change that tool when it needs to be changed, before the 100 hours or after the 100 hours. Remote operations is absolutely essential, and the trend to remote operations, I think, has become very, very paramount and important when we had the pandemic and many of these companies were locked down and had to operate in many different ways. Increasing energy efficiency is a huge opportunity for IIoT, because now we have data that now allows us to understand how individual machines are operating, how collective machines are operating that are interacting through the physical infrastructure of the plant itself. And it also allows us to take advantage of synergistic opportunities between various product operations within the manufacturing process, better coordinate these activities to not only increase energy efficiency, but also help us improve product quality. Next slide, please. The challenges are also significant. Real-time performance in a dynamic environment is challenging. These operating environments in the plant are highly uncertain and are disruptive. And when you're also talking about the integration of humans and machines in the same loop, you need to be able to manage the interaction between these and manage the uncertainties in a dynamic real-time environment. Interoperability is a huge challenge as we look to mix and match devices, including sensors, actuators, and control elements from multiple manufacturers, as well as the protocols that need to be in place for communications. Safety, when we talk about autonomous system operations, is critical, especially when we talk about robotics and collaborative robotics and human interfaces to technologies. Safety is paramount in those environments. Cybersecurity, that is protecting the cyber infrastructure that allows the plant and all of its devices and data to be secure, is essential and is extremely challenging. And very often, when humans embedded in the loop, the humans can become the greatest source for cyber insecurity. Privacy of data. When we think about moving data to the cloud, many of the industrial processes are highly proprietary. And if data from how those processes are operating ever leaks out, very sort of protected processing characteristics and recipes can be revealed, causing extreme opportunities for these industries to be compromised. And again, all of these electronic devices that are providing the connectivity are using energy And so the efficient use of energy of these is absolutely critical, especially those that are being powered through batteries as their source of energy. Next slide, please. Now we move to Industry 4.0 in the next couple of minutes. And it's important, I guess, to look at this slide from McKinsey that really talks about the Industrial Revolution and how we've moved from the beginnings of the Industrial Revolution, pre-1800s, through the idea of the first production lines to looking at the integration of programmable logic controllers in the sort of late 1960s through the early 1970s, and then what we've done today in terms of developing a networked set of physical assets or cyber-physical systems, allowing us to now take advantage of real-time data and analytics in a cyber-physical system operation. Industry 4.0 is essentially just a confluence of trends and technologies that promises through networking of physical assets reshape the way things are made. Next slide, please. Industry 4.0 is a major innovation in digital technology. It has the opportunity to transform energy and manufacturing systems, and the technologies, as you heard before, and probably even in the earlier keynote, are all about advanced robotics, artificial intelligence and machine learning, communications and networking, cloud and edge, IIoT, important areas of data acquisition and analytics, modeling and simulation now become key tools. Software as a service is becoming very, very common, and all of these are embedded in a global value chain. Next slide, please. So we evolve from the standard automation pyramid on the left, where we talk about the management level to the planning level down to the automation technology or floor level, where we then begin to blur what happened in that automation pyramid, where we sort of think about more diverse planning and control applications. We talk more about management execution systems as an information hub in the center to move between production processes and what's happening at the planning level. And now we move to a totally connected architecture of the industrial Internet of Things, where cyber-physical systems are at the core. And we're talking about now all of these things sort of being, without having distinct hierarchies involved, all of these activities are occurring concurrently and simultaneously. Next slide, please. So, as we think about moving from factory evolution of today to tomorrow, we move from sort of more hard automation, which is where we are and where we have been, to what we call sort of soft automation, systems that are self-aware, systems that are predictive, not only predictive of their own behaviors, but predictive of the confluence of behaviors of the cyber-physical system itself. Systems that are self-aware in terms of their health and performance and their activities, and systems that have the ability to self-configure and are adaptable so that they have a true plug-and-play operation paradigm and can adjust dynamically on the fly to changing operating conditions both in the plant and in the environment. Next slide, please. So, in terms of Industry 4.0, the enabling technologies are very, very similar to IIoT, networking and communications, robotics and advanced robotics, collaborative robotics, cloud and edge computing, virtual reality and augmented reality. Automation is key at all levels in this process. Digitization and the digital transformation. We talked about modeling and simulation and computations within the loop. And the whole idea of digital twins, where we use modeling and simulation and digitization to create a digital replica of a process that is data driven, runs in parallel with the physical process, and is used to provide insights through a computational infrastructure for both real-time control, diagnostics, and prognostics. Next slide, please. Sort of close with this idea of value chains. There are two value chains that are important to be considered here. One is the horizontal value chain, which moves from the supplier to the company to the customer, and how this horizontal value supply chain is enabled by digital transformation and the whole idea to simplify and sort of make the process of moving from the supply side through the production side to the customer side much more efficient. It also, we have a vertical supply chain within the company itself, where we now have integrated processes through digitization and sharing and analytics of data that allows us to improve the operating efficiency of the company itself within its horizontal supply chain between the supplier and the customer. Next slide, please. So, I 4.0 opportunities and challenges. There's a great opportunity to reduce operating and production costs by using more data and models that help us better understand the process itself and allow those processes to be more visible and allow us to take advantage of data and methods of analyzing that data to improve our understanding of real-time process operations. It increases the visibility of the process through data and analytics. It improves product quality by allowing us to understand disruptions that are in a process in real time and being able to correct those disruptions and protect the product quality throughout the whole production cycle, from the raw materials to the finished product. It also allows us to embed technology in the product itself to make the products more self-aware, more self-adaptive, and allows the products to also provide data back to the manufacturer when they're in service to help improve the next design of the product. Increasing efficiency and reducing waste are important parts of Industry 4.0 through coordinated activities in the plant that allows us to take advantage of real-time data and analytics in scheduling and local machine control, and then distributed control throughout the plant, which allows us to coordinate activities in a real-time manner rather than a time-based scheduling manner. We now have the opportunity to manage large fleets of connected devices, both in terms of how they operate individually, but more importantly, how they operate collectively as a swarm of connected devices, so that their aggregated or integrated behavior is optimized rather than optimized only on local behavior. We can now optimize on aggregated or more global behavior. Cybersecurity and privacy, as we talked about before, is absolutely essential to protect the devices and systems, but also protect any proprietary data. An important part of Iot 4.0, which is going to be absolutely essential as we move these technology forward, is workforce development and training. This is across the spectrum in terms of how we retrain the current workforce, how we train the next generation of workforce, and then how we develop the next generation of engineers that will not only be developing the new technologies for Industry 4.0, but providing the opportunity for the integration of those technologies into manufacturing plants as they exist and evolve. And then I think finally, organizations need to have a cultural change or a cultural shift. Moving from how we've operated in the past to embracing digital transformation and innovation is not only necessary on the shop floor, but it has to be vertically integrated through the value supply chain, the vertical value supply chain of the company itself. From the C-suite and the highest level executives all the way down to the workers on the factory floor, the ideas of digital transformation and innovation have to be supportive, embraced, and valued. Next slide, please. I'll finally close with the idea of cyber-physical systems. This idea has been developing over the last 10 or 15 years. These are physical assets that are connected both physically, but they're also connected through a communication network. It enables the ability for broader collection of data. It offers the opportunity for embedding intelligence through data analytics and AI/ML and model-based sort of strategies within the devices themselves. And then at the edge level where data is aggregated to allow the devices to better coordinate and collaborate. The devices are endowed with opportunities for control, modeling, and data acquisition functions internally. And they're also self-aware, so they have ideas, they have the opportunity for improving safety, privacy, and security across the devices and the connected enterprise. Next slide, please. And I'll close with the idea of what the opportunities for CPS are. The ideas of improving reliability and resilience through cyber connectivity is a huge opportunity. And we see this now, the importance of this in our energy and utility infrastructure, and I think also in our manufacturing plants. The ability of being resilient, to be robust to disturbances, and being able to ride through a disturbance and maintain maybe not all operations, but some critical operations through those transients and those disturbances to keep functions operational. The ideas of adaptive and self-learning functions, the ability to manage the impact of non-stationary and uncertain processes and disturbances now becomes possible through this connected infrastructure. Real-time data increases the visibility into the physical system and allows us to reduce downtime and increase efficiency, and also provides the opportunity for remote operations, which we saw, as I mentioned previously, very, very important as we navigated our way through the pandemic. Next slide. Finally, security and privacy are key challenges. Safety is paramount and has to be integrated into the design of the cyber-physical system. We talked about interoperability. One thing I didn't mention is time predictability. That is because of the asynchronous nature of the operations of many of these systems, in particular operating in a collaborated environment, the ability to predict, to maintain time predictability begins to slip, and it's important that you have tight time constraints to reduce latencies and improve closed-loop control. Integration of humans in the loop, both from a safety perspective and also from a security perspective, are critical, and how you take advantage of humans in a cyber-physical system is an ongoing research endeavor. Verification, validation, and finally, the social impact of these advanced technologies and how these technologies are evolving to have a significant benefit to society. With that, I will close, and thank you.
All right, Ken, hopefully you can see me. Thank you very much. Okay, awesome. Thanks for the presentation. Unfortunately, we're a little over, so we're going to ask one question, if you'll bear with us before we go on break, but I think it's a good one.
Okay.
With your experiences at Case Western, your experience with working with organization, how is IIoT going at scale? A lot of companies are piloting efforts, but are companies moving to scale at enterprise solutions, and are they realizing the stated business case?
So that is a significant challenge. And in particular, many of the small and medium-sized manufacturing companies that we work with are really struggling with IIoT, both from the device and sensor level, trying to understand what they would do with the data that they achieve, and then trying to figure out how they take advantage of that as they move it to their operations level. I think that the ability of what's the value chain for IIoT, and then how does that actually move to a return on investments or an ROI is a question that the large companies are asking themselves and the small and medium-sized manufacturing companies are asking themselves. And I don't think that the answers out there are to where we would want them to be to see IIoT as a sort of obvious rollout throughout the manufacturing enterprise. So I think that it's early in the IIoT roadmap, and there are plenty of good exemplars out there and examples and use cases that we can learn from. But I would say that from the broad view of the companies, both large, medium, and small that we work with, everybody is still asking those questions, both from the highest levels of what the value is from a sort of return on investment, all the way down to which technologies do we use, where do we deploy them, and how do we take advantage of these opportunities, both on the machine floor or the manufacturing floor, and then all the way through all of the operations in the enterprise.
Thank you very much again, Ken, for your presentation. Thanks for sharing some time with us, and good luck with the program, Case Western Reserve University's overall impact on Northeast Ohio, and thanks for sharing with a little bit of your insights to Southwest Ohio.
Thank you very much. It's my pleasure.
Thank you.
Bye, everybody.